Hello everyone, it's April 29th. Of course we're going to do 30th. Alright. So, today is going to be a tough one and seem to be graph again. So I think what we can expect is something similar, right? Something similar to yesterday. Remove max number of edges. That's exactly what I was thinking yesterday. Right? What we think yesterday is, if I remove those edges, do we still have the full, the graph still reachable for every nodes? That's what I was thinking yesterday. This is slightly different, right? Remove max number of edges to keep the graph fully connected, right? Alice and Bob have an undirected graph of unknowns and 3 types of edges. Type 1 can be traversed by, it's more complicated. Type 1 can be traversed by Alice only. Type 2 can be traversed by Bob only. Type 3 can be traversed by both. Given an array edges where edges I represented bi-directional edge, of type I between nodes and nodes, find the maximum number of edges you can remove so that after removing the edges, the graph can still be fully traversed by both Alice and Bob. The graph is fully traversed by Alice and Bob if starting from any node, they can reach all other nodes. Union find, right? Union find. And then we try to see if we remove a certain edge, return the maximum number of edges you can remove if you cannot traverse the graph. Alright, so what do we say? Well, we have edges that's only traversable. So type 1, type 2 are traversable by 2, and type 3 traversable by both. Right? So in the beginning, 1, 2 have a 3 and have a 1. Which means it's traversable by Alice and by both. This is by both, Alice only, and Bob only. So maybe we can say, okay, for Bob only, what are, and then for Alice only, what are? So in this case, we can say, for Alice only, Alice 1, right? So 1, 2, 3, and 4. So if we go Alice only, it's already all traversable. If like this is Alice, right? And if we go Bob, type 2, that's only 3 and 4. If we go both, that's 1, 2, and 3. Okay? So now we try to figure out what's the maximum number we can remove. I mean, for both, Bob only, Alice only. For one thing, if we have an edge that's Alice and both, then we definitely can remove Alice because both will be better, right? So let's say all these edges can just pre-removed. Like this one can be removed. We don't need this one, right? This one can be removed because it can be replaced by this, right? So the result. So Alice, this can be removed because we can use this. And so Alice is still covered, right? Alice is still covered. And for Bob have 3 and 4. So I can remove. This is another way to analyze. So for Alice, we have 1, 2, 3, 4. Okay, so Alice is already done. And for Bob, we have 3, 4. So maybe we say, okay, we need to make Bob, right? And to make Bob, I need to use the edges that's for both. So for both, if I add edges to 3 to Bob, and add edges and 2 to Bob. Now Bob is, so adding both, now Bob is all good. So these are definitely needed. And these are all shared. So yeah, this can be deleted because Alice has this as well. And Alice has 2, 4. And Alice has 2, 3. So this can be deleted. This can be deleted. 1, 2, and a 1, 3. Yes. Okay. Okie dokie. What's the second example? Ah, this is good. All right. How do we consider this? Like I said, right? For all the edges that has duplicates with type 3, we can remove those because we don't need both. Okay? And what if we have both type 1 and type 2 connecting the same two nodes? Yeah, we probably have to keep those, right? Okay, so if we do that, right, then in this case we have 1 to 2, we have a type 3, and 1 to 3 we have a type 1, 2 to 3 we have a type 3, 2 to 4 we have a type 1, and this we have a type 2, right? So if we have a type 3, we use type 3. Otherwise, we have to stay type 1 and type 2. So in this case, we can say, okay, type 3, we can connect 1, 2, 3, right? So this is from type 3, we can get 1, 2, 3 together. So we cannot get all of them together. So we need to see what what paths that gives you. Like say we want to go for Alice. So for Alice wants 4, right? So we need to see if there is a path that goes to 4, because this is all connected. So anything connected to 4 will work. So we see Alice has 1. This is Alice going to 4. So we say, okay, so 2 to 4, this edge must be kept. So these are all kept, right? So this edge must be kept. And Bob wants 4 as well, right? Bob wants 4 as well. So we say 4. Bob has a 4, so this needed. And then we know this one can be eliminated as well. So that's why we have 2 eliminate. Okay, so let's try this example. We have 1 to 2, that's type 3. 2 to 3, type 3. Okay, 1 to 4, type 1. And 1 to 4, type 2. So again, for both, right, we can conclude 1, 2, 3. Right, 1, 2, 3. So type 3, we get both. So now we say Alice wants 4, right? Alice wants 4. And for 4 for type 1, we have 1. Okay, so we have to keep that. Okay, we have to keep that. And for Bob, I want 4. Bob wants 4 as well. And Bob's 4 has only 1, so we have to keep that. That's why we cannot remove anything. Okay, what's the last example? Last example is this 1. That's type 1. Type 3. Type 2. So for both, we have 2 and 3. So Alice wants 1 and 4. And they have to connect it to 2 and 3. So we need to look for from 1, right? From 1, does there exist a path from 1 to 2 or 1 to 3? 1 to any of these, right? And we say 1 to 2 have a type 1. That's for Alice. So this exists. That's good. So 1 is done. Okay, so we know this one has to be kept. So now we have to go 4. Okay, 4 need to go to 2 or 4 need to go to 3. And we see 4 only go to 3 and it's type 2 Alice cannot use. There's no 4 to 2, so there's no way for Alice to incorporate 4. So that's not possible. Therefore, this one returns to -1. So what do you think? We graph it for sure, and each graph we can have the key, right? It's going to be a default dict, and inside I think another default dict of what? Nodes, right? 1 to 2, type 1, type 2, right? 1 to 3, say type 1. Anyway, I can just use this, it's fine. Right? And then when we check, we union find everything that's type 3. Okay? We union find everything that's type 3. Yeah, so we go through everything. If it's type 3, we will keep it. Right? If it's type 3, now we don't go into this. All type 3 will be contained unless it's duplicated. Unless it's duplicated. How do you know it's duplicated? Well, we are connecting them, right? Union find. If one of them, if we have a path that's already unioned, okay, so you union, you get a path, you union, get a path, you union, and if a path is already union, that means that path is not necessary, so we can remove that. So we go through all type 3, right? We get all of them, and then we get this both, okay? We get both. And then we need to know what is missing, right? What is missing? So we can just go from 1 to the end and see if it's missing. If it's missing, we go to this adjacency list, not adjacency, we go to this graph, okay? And to see, because we have what is missing. Oh, how do we know what is missing? I have a set, okay? Every time we connect, we remove those from the set. So at the end, we'll have, say, the unconnected, right? Unlinked. We have an unlinked set, right? We'll have all the unlinked nodes. Then we go through these nodes one by one, okay? And each one, because it's unlinked, right? So for each one, for each unlinked, we need to know if it has a connection with the one that's already in it, right? If it does not have a connection with one already in it, then it's impossible for it to be connected. Hold on. It might be connected to something else, and something else has a connection into it. That is correct. That is correct. So what do we say? What do we say? So we have a both, right? That's not. But we get rid of all the type 3. So we can go through all the type 1. Okay, how about we do that? We go through all the type 1. And as we go through type 1, we see the 2 nodes. If they're already in it, that can be eliminated. If they're not, then we incorporate it. It's an interesting thought. That is an interesting thought. We incorporate it, right? and then we just go through the end, see if we can incorporate everything. If we can, that means we're good. If not, then it's not good. You want to give that a shot? Yeah? Let's give it a try. So, okay, let's summarize what we think. Here's what we think. We will create two DSUs. Okay, we have a DSU A for Alice and a DSU B for Bob. So we will go through, right? We'll go through all type 3s. All type 3 links, edges. And we'll populate, right? We'll populate both DSU A and DSU B. Okay, it's the same. And for this we can count, right? And we can count the number of edges used. Okay, let's not count the number of edges used. Let's count the number of edges not used, right? And you can say and count the number of edges discarded, and we discard if a link is already exist. If the two nodes are already inside the group, then we can discard if they show up again, right? And then we go through, right? We go through all type 1, okay, for DSU A, doing exactly the same thing as this, right? We're doing exactly the same thing as this. And the answer is what? The maximum number you can remove. Yeah. Go through all type 1 for this. And then we do same thing. Go through all type 2 for DSU B. And we follow exactly the same logic. Let's give this a shot. This might work. Might. All right. So, oh my God. Hey, more practice is always good. Parent. Find. If the parent is not equal to x, then find self.parent x. Turn self.parent x. Union. Oh, this is Boolean. This is where the Boolean comes into play. Yep. Parent x, parent y. If px is not equal to py. Okay. If rank px larger than self.rank py self.parent px equal to py equal to px outlive self.rank px smaller than self.rank py self.parent px equals py else self.parent py equals px self.rank px plus equal 1 return true, return false. All right, so I can say DSU A, DSU B both equal to DSU n dsu n. Okay. We need to go the edges. Discarded because 0. And we're gonna get a 3 first. Why don't we sort it? Well, sort it will go O and log n. Do you want O and log n? I am not sure. Let's do this. Edges A, edges B. This and this. Okay. Then we say for type AB in edges, if t is equal to 1, edges A dot append AB. If t equals to 2, elif t equals to 2, edges B dot append AB. Else, now this t equals to 3. Then we say if dus dsu, if dsu A dot union AB is true, if it's false, which means they're already doing it, then discard it plus equal 1. And dsu B dot union AB. This is the same, because these two will be the exact same. So we do this. So completely take full advantage of all type 3 edges. And of course, we discard the ones if we don't need it anymore. So we do this. Okay. Now we're gonna go through for AB in edges A. Okay. We say if not dsu dot union AB, which means this node is no longer needed, discard it plus equal 1. If it's needed, we don't do it. And then for AB in edges B, if not dsu B dot union AB, discard it plus equal 1. And then we return discarded. I don't know. We'll see. Zero. Oh, the last one might not be right. And the last one will become... Holy crap, how do we do -1? We'll figure out a way to do -1. Don't worry. List out of range. That is interesting. Oh, the nodes start from 1? Plus 1. Yep. So this... What do we say on this thing? How do we know that... Well, I mean, if dsu A does not contain right? If not all of them has, then how do we know? We have to check? Damn. What would be the better way to detect this? It has to be ON to finally detect it. There gotta be a way. There gotta be a way that we can know immediately if it's good or bad. I guess. I don't know. Can we know it? I'm gonna use a stupid way, but how can we tell? How can we tell? What's the difference between not and yeah, I guess there's no other way. We just have to say for I in range, my god, 1 to n plus 1. I really don't want to do that. Can say num of partition, num of groups, group A, group B equals set and set. How does this look ugly? Group A dot add dsu A dot find I, group B dot add dsu B dot find I, compress them, and then say if len group A equals len group B equals n, else minus 1. Huh? Oh, that's equal to 1, because you only have to have one group. Check if all the nodes are connected. I feel like there gotta be an easier way to do this, right? There gotta be an easier way to do this. Maybe what we can do, you know what? How about we don't do this? We just do this and do this, okay? And then we just say len set self dot. But then we have a 0. Gosh, you gotta be kidding me, right? Then we have a 0. Oh, it's fine. It's fine. It's fine. Dot parent, okay, equals this len self dot set self dot parent. Who's parent? dsu A, the parent. dsu B, the parent. Equal to 2, right? The total number of groups in the DSU must be 2 because there is no, because node 0, right? Node 0 is not part of the graph. Yeah. I don't know. What do you think? You think this will be right? Well, I hope. I'm afraid is this last check might take more time than we want. Anyway, just give it a shot. Oh, okay. I got the April badge. Consistency is key. I feel like it should be consistency is the key. See you next month. All right. I guess. Yeah, I mean, that helps, right? The challenge from yesterday definitely helped this tremendously. Because it kind of point us to the right direction. Challenge yesterday, right, definitely helps because it points us to the right direction on solving this problem. Immediately I go for union find to check for connectedness. There's also a bit greedy here because I always want to use type 3 edges first, right? And after exhausting all type 3 edges, we then try to put in type 1 and type 2, and type 1 and type 2. Use two separate union find for Alice and Bob. We include edges that connect nodes not connected already and discard the ones that do not that connect nodes that have already been connected, right? This way, the final node edges included are the minimum amount of edges to allow the graph to be connected. That's the key. Okay, so we have ON for all the OE for all the edges, plus ON to set up union find. I mean, this is OE, this could be OE, this is OE, and we can say OE times, and also plus E times union, which, and plus N times find, right? Union and find. But it's fine. These we can just consider, if union and find, we consider O1, which we can say this is just equal to O E plus N. Okay, check the solution. Union find alpha N. Oh, I mean, that's just this one, right? A new pattern, 3 hearts per week. Yeah, Friday, Saturday, and Sunday. DSU, that's good. DSU is good. We always need DSU. Yes, one for Bob. Yes. That's correct. How can I find the edges? It's useful. Very useful solving. Yes, it's very useful. Extremely fast. Inverse outcome and function. Okay, DSU to perform the union of two nodes of the edge, and if the nodes are not connected earlier, yes. Every edge, if the two nodes were not connected earlier, we know this edge is required. To get the answer, we can subtract the number of required edges from the total number of edges. So we need a minimum number of the type 3 are the most useful. So we'll first iterate over type 3. And for these edges, we'll add the edges. I wonder if we don't use these two, maybe it'll be faster. I think we are on the correct path. Is connected. How do you check that? Where is connected? Components equal to components. Oh, int components. Interesting. Components minus. Oh, that's good. DSU. This is DSU 1. Let's go DSU 2. That's something new. DSU 2. Okay. This DSU contains info about the number of components. So we don't have to compute it again. Self.components. I think that's happened here, right? If they are the same, if they're not the same, then we are reducing a component. Exactly. Self.components minus equal 1. Right? If two nodes need to be unioned, right, the number of components number of total components must decrease by 1. So with DSU 2, this is update. Use DSU 2 where we keep track of the number of components in DSU such that we don't have to check at the end. Make it faster, which means we can eliminate. We don't need this one anymore. So the runtime is going to be we don't need this. That's why it says the runtime is E times outcome n. So that's why. Okay, so we're gonna do DSU 2, and also we won't bother accumulating edges A and edges B. Separating type 1 and type 2 edges, right? In additional space. yeah, it doesn't really help. So we don't do this, okay? So we just do type 3. If t is equal to 3, then we do this. And we're gonna do tab again, okay, in edges. Then we say if t is equal to 1, right, we do this. If t is equal to 2, we do this. Right, so we don't have to do this. We just say return discarded if dsu a dot components is equal to dsu b dot components equal to 1. Okay, let's give this a shot. See if this one is right. Two. The final number of components is 2 because node 0 is not in the graph. There we go. I think this will be faster. We saved 1 round. I might just leave DSU2. Just get this one out. Ah, 100-ish millisecond. Good. That's good. Okay, that'll be it. I have other things tonight, so I'll just end it right here.